terminology your book uses is standard terminology and analysis. What we're doing here is, with this limit, we're restricting x to this interval. Then a little bit later, we're restricting it to this interval. Then we're restricting it to an even smaller interval. So you have this sequence of intervals. If I don't color code, this side is always a 0, and this side is smaller and smaller intervals above 0. When we do this, we can think of a good space to do this. I don't need much because the picture's pretty obvious. Okay, here's our origin. We just restrict to smaller and smaller circles, right? By letting delta be smaller and smaller. And that restricts this expression. Okay? We call this, well, these are circles, okay? These are delta circles of radius delta. If we go to 3 dimensions, we get spheres. Spheres of radius delta. Okay? And that's a ball. If we go to higher dimensions, we still call it a ball. So if this is 1 over x squared plus y squared plus z squared plus w squared, 4 dimensions, we just say, okay, square root of x squared plus y squared plus z squared plus w squared is less than delta. And we draw the conclusions, and the algebra is almost exactly the same as it is for 2 dimensions. You can't visualize it anymore. Now you can visualize it in 3 dimensions, spheres, and your distance in spheres would be x squared plus y squared plus z squared, right? If you want 100 dimensions, okay? Then you run out of letters in the alphabet, but then you just call your variables x1, x2, x3 up through x100. So it'd be square root of x1 squared, x2 squared up through x100 squared. Still make the same argument. Okay? Okay, well, so the terminology you see in the book, and the book, you know, the book does it. I haven't checked whether Thomas, Thomas's book might be approaching 70 years old. Okay? Terminology and the notation for limits, standard notation hasn't changed. Probably hasn't changed in 100 years. Because the whole theory was worked out over 200 years ago. It takes a while for notation to settle in, but I would bet, I haven't looked at a 1920s mathematics text, an analysis text or calculus text, but I'll bet you would find very similar notation. Go back into the 1800s, notation was still sorting itself out. Then I wouldn't be surprised if the notation was standardized by 1850, pre-Civil War. Okay, well there's the picture, and I'm gonna let you read it in your textbook, and I do want you to read the section, so you understand. Now, in practical purposes, if you have something like this, where this thing is a continuous function, doesn't change much if you change x and y by just a little bit. And if the function's defined at this point, then you can pretty much conclude that the limit is whatever you get when you plug in these numbers. Nothing weird is happening in the neighborhood of 1, 1. The only weird thing that happens to this function is near 0, 0, where its value approaches infinity. If it was 1 over x plus y, the value would not have a limit, because whether it approaches positive infinity or negative infinity depends on how you approach the origin. Reiterate that important idea. So what about, there are some rules that you can use for evaluating limits.